Exactly. Yeah. Because both were invited to come here and for different reasons, but very, very serious reasons, they both couldn't come. So exactly, yeah, that is already a very good reason. It's clear. So we decided to make a special session in which everything will be by Zoom and we will host their talk. So let's start with Jean-Yves Desaules from the Institute of Science and Technology of Austria. And the title is long, and they don't see the third. Okay, slow thermalization but fast transport. The one lattice gauge theory as a unique paradigm of ergodicity braking. Jean-Yves, you can go.
Thank you very much for the invitation, and I'm sorry that I couldn't come. But yeah, I'm very grateful for the accommodation and for being able to still present online. So yeah, today I'm going to talk about the Yuan lattice gauge theory in the context of thermalization. And this will, at the end, follow results of a recent preprint that has been on arXiv earlier last week. So if you want more detail, go check it out. So maybe a quick intro about what I'm going to talk about. So first of all, I want to discuss a bit what we mean by quantum chaos, quantum thermalization, because all these words get thrown around kind of interchangeably, and why it's a bit more subtle than this. And then I will discuss how this Yuan lattice gauge theory violates either thermalization, ergodicity, in very specific way, and why it's kind of the perfect model to study violation of thermalization. So first of all, a bit about quantum chaos / thermalization. I mean, usually when we talk about this word, we think about a number of things that are believed to be universal for local Hamiltonian without any special structures. The first one is level repulsion in the energy levels, right? Where we have something that is GOE, so Gaussian orthogonal ensemble, and that is far away from the Poissonian distribution. Alternatively, we often talk about thermalization, we refer to the eigenstate thermalization hypothesis, or the ETH, where now what we care is not really the energies themselves, but the properties of the eigenstates, and the fact that at the same energy, they have the same properties, which are the properties of thermal state at that energy. And finally, maybe less common, but still very, very well studied property of chaotic system is diffusive transport of all quantities, of all conserved quantities, let's say. If you look at some local conserved charge and you look at the out-of-time correlator, you expect things to decay as t to the -1/2. And if you look at the full profile, you see that things do not fly ballistically, but show diffusion. And that's basically a symptom that there is no structure, there's no quasi-particle that can fly ballistically, but instead everything is strongly interactive. And why do we usually merge these three together? Well, it's because if I take a random local Hamiltonian, well, I have all these three things kind of for free. This is expected with probability 1. And at the same time, if I take something that we usually think as violating this, let's say something that is integrable on MBL, which has an extensive number of conserved quantity, in general, I break all three of these properties. So in most cases, there's not really any reason to distinguish, but we know from a lot of studies that this is not so black and white. And for example, if we forget to resolve conventional symmetry like translation, this has not really any bearing on the ETH or like diffusion of conserved quantities, but surely enough, it will affect your level repulsion, and you will quickly see this in the distribution of level spacing. Conversely, I can have some weak ergodicity braking, like weak Hilbert space fragmentation or quantum many-body scars, where I won't really see it on any global quantity, but the ETH will have a visible violation, at least the strong ETH. And maybe a bit more unusual are things like special conservation law, like higher moment conservation, let's say dipole conservation, where even if you resolve them, which gives you level repulsion ETH, you will likely get something that is not diffusive, but slower, so sub-diffusive. And this is the last bit that's perhaps the most interesting to me. And it belongs to a class, so this higher moment conservation can be broadly taken into kinetically constrained models. And these kinetically constrained models are a very large family with many, many properties. You could have things that violate level repulsion when you have strong Hilbert space fragmentation, or you could have quantum many-body scars due to kinetic constraints, which violate ETH, or you could have special constraints like this higher moment conservation that give you sub-diffusion. So I think this class of model is a very nice field to play with and to study thermalization with violation. And within this family, I want to focus on one specific model that hosts kind of all of these phenomena, or almost, which is the U1 lattice gauge theory. And so let me quickly introduce lattice gauge theory for those of you not too familiar. Basically, there's a way to put high energy physics, so like the standard model, onto a tabletop. And for that, in particular, we take particles and we put them on a lattice. And specifically, what we have is that on the sides of this lattice, we have matter. So for example, quarks, if you want to study quantum chromodynamics. And then on the links between them, mediating their interaction, you have the gauge field. So for example, gluons here. And basically, you go from a quantum field theory, which is almost intractable, to something which has well-defined, let's say, particles, sites with well-defined interaction that we could use standard tricks of quantum many-body. But what's interesting is, since you come from some specific gauge theory, you still preserve this structure, this gauge invariance, and it's manifested as some kind of constraint between the interaction of these particles. And so that's basically a very natural, a very physical way to have a model with kinetic constraints. And I want to focus on one model in particular, which is the U1 lattice gauge theory in one spatial dimension. So what is this model? Well, basically, it's a simple representation of quantum electrodynamics that we can get. And it's called also the lattice finger model. And so basically, as before, you have this lattice, and on site you have a particle, in this case, which are electron or positron, so charged particle, because we want to do electrodynamics. And in between them, you have this electric field. And so this is the Hamiltonian that describes everything. So notice that you have some fermionic creation annihilation operator, so for the electron and positron. And you also have the field here, which is situated on link, which mediates the interaction between these electrons and positrons. And you also have clearly the value of the electric field on the links for the electrostatic energy. Now, I'm looking at the simplest possible case, so we can forget about all this. We just want to see the dynamics, so how these particles and these fields evolve in time. And well, this is relatively simple Hamiltonian as it looks, but one thing that is hidden within it is, again, the gauge invariance, and in this case, it's Gauss law that we all know. So for each particle, so each fermions, we have this law, which basically tells me if I take the electric field that exits minus the electric field that comes in, or position that comes in, well, it should give me the total charge that is hidden within it. So it's really just Gauss law as we know it. It's just written in a very weird form because we have these terms here which come from the fact that we have staggered fermions. This is to avoid some problem called as fermion doubling, which I will not go into detail because it's not paramount. But the thing to understand is that we really have these fermions, and Gauss law is as usual. So what we have is here we can see, for example, a field configuration, and we can look at a particular size. So field goes in is the same as a field that goes out. We have nothing, so we don't have any of the particle. But if the total field is positive, we have a positron, and if the total field is negative, we have an electron. And the only thing is that you can only have electron on the even side and positron on the outside. So that's just a weird oddity, but it's to recover the right model in the infinite, the continuum limit. So yeah, just quantum electrodynamics. And then what does this term do on this configuration exactly? Well, it changes the field here, for example, and in turn, changing these fields create a positron-electron pair. So it's fairly straightforward. So now we have a model that we can put on a lattice, so we can see what it does, we can understand physically. But how do we deal with this U1 field, which can take an infinite number of values? Because this is still quite complicated to deal with, we would like to have a finite Hilbert space. Well, what we do is simply we truncate it. So we say, okay, this U1 field, like the electric field, can now take only a finite number of values. And the only thing we need to be careful when we do that is that the commutation relation between the field operators stays the same, namely this one. But this is very familiar, we recognize it. It's like U is a ladder operator for E. So we can just say, well, okay, we just make these spin with spin S with some arbitrary value. And this is exactly what people do. So this is a common technique. And the only trick is that we kind of stagger these spins to match the staggering of the fermion. Again, that's really a detail, a technicality. It doesn't really affect the results. The point is that we now have fermions on the sides and spin S on the links. And then we can ask, okay, we have this nice spin. What happened to them? How is Gauss law implemented? So we go from this, where each of these operator needs to be 0 to guarantee that if we integrate the field, we get the charge inside. We get this kind of simpler formulation. So if we take two consecutive links, their sum must be this. But this quantity is always plus or minus 1/2. And so basically, these two must always sum to 0 or -1. And that's all there is. This is just Gauss law. So it's a very simple constraint. And actually, if we now look at the model again with the fermion and the spins, so before it was pointing right and left to show the field, now I'm pointing up and down to show that these are spins instead. It's essentially the same. Now the model is even simpler. If I take two links, if their spin sum to 0, I don't have an electron or a positron. And if their sums is -1, I have either a positron or an electron, depending if it's an odd or even sign.
Sorry, just to be sure.
Yes.
You put, let's say, arrows up, arrows down, but these are spin S, right? So they take S possible value. Okay, okay.
Yes. So for the moment, I'm just showing this example with spin half, but yes, what matters is really just their sum here.
Yeah. Okay, thanks.
Okay. And yeah, the constraint is that they must sum to this. But now what you can see here is that if I give you the configuration of these spins, well, for each of two of them, you can sum them up and tell me, oh, it's 0, I don't have a particle, or oh, it's 1, I have an electron or a positron. So in fact, all the information about the matter, so the fermions, is completely redundant, and I can completely get rid of it to get a pure spin model. And well, the last thing to know to get the spin model is what exactly is the dynamics of these spins. And we've seen before that the dynamic is a creation of electron-positron pairs. And what this is in terms of the spin is just single spin flips between the electron and positron. And so in the end, we went from some complicated quantum field theory to a simple spin model that I can write down like this. So it's single spin flips on every possible link, but now there is a constraint with these P's. And what this constraint does is that it guarantees that when I flip this spin, I don't violate this constraint. So if I'm flipping this spin, I need to check that these two respect the constraint and these two respect the constraint. And so in the end, this means that the constraint is local. So my Hamiltonian is strictly local, but because of the constraint, it's interacting. And in fact, for every single value of S, the model is non-integrable in the sense that we have strong level repulsion. we don't find any special conserved quantity beyond, let's say, energy translation and other things like this. So we have now simplified quantum electrodynamics to this model, and we can ask, what are these properties? And this is now where we come to the quantum link model, which is the model I just showed you. And first, let me talk a bit about the spin 1/2 case, right? Just to show very quick examples so you can kind of get a bit of intuition about what we get after all this transformation. And so let's look at two consecutive spins. If they're both down, we get -1, so that's allowed. If they are in opposite direction, we get 0, and that's still allowed. But if they both point up, then this is forbidden. And for a lot of you, this might be familiar, this constraint, because it's exactly the constraint of the PXP model, which has been widely studied in the past, let's say, decade. And this model shows up in plenty of places. For example, it also describes dynamic in Rydberg chains in the regime of high blockade. So it's perhaps not too surprising to find it here, but still. This model is famous for one thing, which is quantum many-body scars. And as a quick recap, quantum many-body scar describes the fact that while a model is non-integrable and thermalizes for most initial state, you have a few specific configurations that if you quench from, you get very slow thermalization in the form of oscillation. So the wave function comes back to itself periodically. And so we have it in PXP, so we have it in the spin-half quantum link model. And the first question we wanted to ask was, does scarring persist for higher value of spin? So for now, I've just talked about spin-half, but what happened when I put spin higher than 1/2? Does everything collapses? Do I get no scarring? Do things become completely chaotic? Well, this is what we looked into a few years ago with a team of collaborators. And these are the results of the same kind of quench for different values of the spin. And what you see is that, indeed, for all cases, you have one state that shows clear revivals, while other states thermalize very quickly. So we do get scarring for all values of S. But you also see that this peak gets weaker and weaker, and this is for similarly sized Hilbert spaces. So actually, scarring seems to get weaker as spin increases. And in fact, another problem with this is that the initial state from which you have scarring is away from the physical part of the Hilbert space. And what I mean by this is that if you take spin to infinity, you recover the full U1 quantum link model, right? Because you no longer truncate your U1 field. But here, the initial state from which you get scarring always has extremal value of the field. So whatever you do, even if S is super high, the dynamic will still feel the truncation immediately because you are at the boundary at which you can no longer go further up or further down. So this state is not representative, the dynamic of this state is not representative of the infinite S limit. And so our first finding for this was that while you have scarring in the spin S quantum link model, it's not coming from the lattice gauge theory, it's not coming from the Schwenger model, it's instead a feature of truncation. But now, what I want to show you is that this is not the case for another expression of, let's say, avoided thermalization. And by that, I'm going to talk about transport of energy, so away from diffusion. So first, let's again go to the spin-half case. Again, a few years ago, we looked at transport in the PXP case with other collaborators. And since this is a constraint model, we're hoping to see if transport was subdiffusive, as was found in several other models, like for the Motzkin chain and the Fredkin chain and other of this model. Unlike this model, we don't really have spin. All that we have is conserve is energy. So we look at transport of energy. And once again, we look at this out of time connected correlator. So basically, the idea is like you put a bump of energy in the middle of your chain, and you see how these bumps decay over time. and you expect it to decay as a power law. And if it's ballistic, it will be T to the -1. If it's diffusive, it's T to the -1/2. And we studied this, and we found that at long time, indeed, we're recovering a power law, because this is a straight line in a log-log plot. But what was extremely surprising is that this power law didn't go to diffusion, so didn't go to 1/2, but instead was super diffusive at all times we could probe. And here, seemingly going to 2/3. And this was extremely surprising because we were expecting diffusion of subdiffusion, and what we got was super diffusion. And in this work, we were not able to really conclude where this was coming from. We had many hypotheses. One was that it's linked to scarring, because this oscillation at short times are linked to scarring. And another hypothesis was a proximity to integrability. But we were never able to show for sure where this was coming from. And now we see that the quantum link model is actually a perfect model to test this. Because if you go to spin 1, your chances of being close to integrability are basically, well, in a random model, 0. And at the same time, we have just shown that scarrings get weaker. So if we get that transport becomes diffusing immediately for higher spin, we know that it's likely one of these two. But at the same time, if we still get super diffusive transport at higher spin, we know that these two explanations are likely false. And so in our last work with collaborator at ICTP in Trieste, this is exactly what we did. And we found something which was very surprising, which is when you go to higher spin, you get even faster transport. And this is despite the model being more constrained. So here you see results for spin 1, 3.5, and 2 from ED. And you see that, well, spin 1 is super diffusive, and spin 3.5 and spin 2 are extremely close to ballistic. So, and we also did some tensor networks results for spin 1, and we found that at intermediate time, it looks again super diffusive, but maybe goes to diffusion at very, very long time. Nonetheless, we find something that is not diffusion at short times, and we clearly don't find subdiffusion. So this seems to rule out scarring and proximity to integrity for transport. And well, this was very curious, and we wanted to check if this was generic to PXP type constraint. So we checked another generalization of PXP to higher spin. The exact model is not really important. The point is, for the different generalization we tried, we got diffusion immediately. So here you can see like spin 1, 3.5, and spin 2. And even at short time, you get T to the -1/2, which are these lines here. And again, we did tensor network method, extremely clean diffusion. So this tells us that the quantum link model is special. It's not just any constraint that gives this. It does this model has something more. And so it's really important to understand what it is and how we get super diffusive transport in it. And the key to understanding why this model is special is actually to go back to the fermions. Because until now, all I've shown you is in a model where we have integrated out fermions to just get a pure spin model, which is super convenient for all kinds of simulation. But actually, if we have open boundary condition, we can do the opposite. We can integrate out the spins and just end up with a fermionic model. So the boundary spins are always frozen. But if I know the value of this frozen spin, and I know if there's a particle here or not, well, then I know what with Gauss law, I know this one. And then if I know if there's a particle here, with Gauss law, I will know this one, etc. So coming from the edge, if I know the boundary spin and I know the fermions, I can get rid of my knowledge of all the other spins because I can always reconstruct it. And so in the end, what I get is basically fermionic hopping model, which I can turn into a spin XX model via Jordan Wigner. And so this is, again, a very simple model with constraints. But now the constraint is very, very different from the case of the quantum link model. For one thing, the constraint is non-local. As you see, each of these quantities depends on the sum from the left of the chain to some site. And this is due exactly to what I show. To find the value a spin can take, I need to start from here and keep track of all the fermions until arrive at my spin. And that doesn't seem very nice to have a non-local constraint. But now what I have is that the constraint becomes weaker and weaker as the spin increases. And when I get to infinite spin, I actually get the unconstrained XX model. Actually, for finite size, there's this condition, but if I have S, which is infinite, I recover the free XX model for any L. And in the free XX model, we know exactly that things are supposed to be ballistic, that transport is supposed to be fast. And so what this suggests is that while scarring is not coming from the Schwinger model for infinite S, the fast transport is, and has a completely different origin in that model, in this model, including in PXP. And another interesting consequence is that this model has not just energy, which is conserved, it also has spin, which is conserved. And we can check if spin transport is ballistic. And we find that indeed, already at spin 1, we get ballistic spin transport at all reachable time. So again, this kind of tells us that it's very likely that all this anomalous transport we see is surviving all the way from the Schwinger model and is not a feature of the truncation. So to summarize, the U1 lattice gauge model has a rich physics. It has both quantum many-body scars and anomalous transport, but these come from very different origin. Scarring seems to be really caused by the truncation and gets clearer and clearer as you truncate more. So it's stronger for PXP, which is spin half. At the same time, energy transports gets faster as is increased because you get closer and closer to the unconstrained XX model that you get at infinite S. And also that this constrained XX formulation reveals that we don't just have energy, which is conserved, we have kind of a hidden U1 charge, which also has ballistic transport. And the next step to study all of this and to see if this theory is indeed true is to look at local interoperability breaking perturbation of the XX model to see how they affect transport and scarring. And with that, I just want to thank my collaborator at ISTA, TUM, and ICTP, and remind you that if you want more detail, feel free to check our preprint on archive, and I thank you for your attention.
11:30 is probably the only talk in the entire event that remain of time. So let's go with a few questions. I can perhaps go with one. I mean, you say that, let's say, the scarring phenomenon is probably not robust in the real Schwinger model.
Yeah.
But essentially, the argument that you bring is that, let's say, the state that experience the scar dynamics is, let's say, a highest weight, so it's very close to where the truncation is, right?
Yes, it's exactly where the truncation is.
Okay, but I was wondering, this is just the state that feel the presence of the scars, but the scars are not necessarily, let's say, close to the truncation point. So how this rule out the scars in the real model? I mean, I understand that, let's say, the state that feel there is close to the transition, close to the truncation.
But if you don't have this truncation, I mean, it's a bit tricky with the fact that you take a limit here, but the reasoning is that if you don't have a state that can fill the scarring, then you don't have the scarring, right? I mean, if S is infinite, there is no truncation, so there is no such state. So there's no, let's say, clear traces of the scarring. And also maybe one other thing is that if you look at the spin, so this is this maximum minimum weight, but in terms of the fermion, it's just a vacuum where you have no positron, no electrons. And other configuration with no positron and no electron thermalize extremely rapidly. So from a physical point of view, if you just look at the matter fields, as you go to larger S, you have more and more of this vacuum configuration, the one with, let's say, low field. And also, and the only one that gives you scarring is pushed further and further away and is getting, let's say, overwhelmed. You're just one among exponentially many other vacuum configurations. So
So would it make sense to, let's say, to start from the PXP and you have the special eigenstates, and then you increase S and you, because you should see that the special eigenstates become more and more thermal by increasing S, right? So does it make sense to make such a check, or maybe
I
not?
mean,
Because
so we have looked at the eigenstates, and things get worse in the sense that in PXP you have really a set of like a linear number of eigenstates that are extremely well separated from the thermal bulk. But as you go to larger S, you have kind of bunches of states which are less prominently separated from the bulk. So scarring gets a bit dirtier with kind of, instead of in one special eigenstate, you have like a concentration of eigenstate in energy.
Okay.
So in a sense, it is getting more thermal, but that's much harder to, let's say, quantify than the dynamics.
I see. Okay, thanks. More questions? Yes, go.
So, so you obtain the XX model by first doing a mapping in which the constraints become non-local, and then saying that for S that goes to infinity, you can just ignore them, right? But in principle, you could do the same thing directly on the PXP formulation, yeah, on the PXP formulation, and then take large S of that thing. Am I wrong?
I mean, so this model is equivalent to the quantum link model, right? Except for matrix element. It's just two different way of seeing it, but it's exactly the same model here for the finite S.
And in here, the constraints are non-local.
Yes, in terms of the fermion, the constraint is non-local.
It's complicated if you want to do a large S expansion beyond the first order in 1 over S, right? Because at first order in 1 over S, you say the constraint just loses its role.
Sorry, could you repeat that? I'm not sure I quite understand what exactly is a question.
So my question is, do I understand correctly that you in this formulation you have the projectors are non-local, and then you say that when S goes to infinity, the projectors just disappear?
Yes, because I mean the projector limits the value this can take, but if S is infinite, this can take all values basically, and so you're not constraining anything.
But this does not allow you to compute a 1 over S expansion of that Hamiltonian.
I don't think you can do it that way, but
going back to the origin, to the other formulation, equivalent one, then you should get the same thing, right? You should get that if you do a large S expansion, the first term should be the excess model, and then you are going to have 1 over S corrections.
But you're not looking at the same degrees of freedom, so.
But we are looking at the same Hamiltonian.
Sure, but I mean, these are dual formulation, right? But I mean, you should get indeed the same model, but seeing that directly from the expansion might be highly non-trivial. So I'm not sure exactly how to answer your question. Like yeah, this, I mean, here we just have the gauge field. The other one, we only have the fermionic field. They both encode all the information because both are redundant, but they really behave differently. Like this one is local, but the constraint becomes stronger with larger S, whereas the other one, things are non-local, but the constraint is seemingly smaller with larger S. So they are really very different formulation of the same model. So translating from one to another is really non-trivial, I would say.
Okay.
Yeah, I have one. Hi. So is your guess essentially that as you increase the truncation, the transport is like almost ballistic for longer and longer, and then eventually just goes to diffusion?
Yes.
Yeah,
that would be what we expect. Like the quasi-particles are more long-lived, but we we are kind of limited with numerical data because since the XX model, which is less constrained, still is non-local, right? Like we do all the tensor network simulation with the quantum link model formulation that gives the same.
It's gonna get harder, yeah, but I guess
Yeah.
just looking at like that inset where you had the time dependency.
Yeah.
For the R, I'm looking at your paper, R equals 2,
Yeah.
I don't know what truncation that is, but like.
Yeah,
you're
it's,
really-
it's S equal 1, R is 2S. Yeah.
And yeah, okay, so probably what's happening is it looks ballistic at early times and then goes over, but then maybe there's some, if you could do some like supernumerics, maybe you could even like collapse as a function of S or something and figure out what the time scale is as a function of S. That would be nice, but.
Yeah, that would be nice, but at the moment we really cannot say anything about what the scaling of this is. We can only say that at very early times, if you look at different curves, they really go closer and closer to ballistic, and as soon as you're S equal 2, you stay at the ballistic point. And also maybe perhaps, I mean, it's not the same system sizes, so there are a lot of things to see, but in PXP, so in spin half, we maybe see something that is slightly slower. So it might not be as easy as, you directly get a nice collapse for 1/2, 1 and 2. You might need to, let's say, go beyond the special case 1/2 to see something that goes smoothly to large S. So there might be some finite side effect for small S.
Okay, thank you.
Okay, so I think it's time to switch gears. So Jean-Yves, you can probably, let's say, stop sharing and Sona can take the lead.
All right. Do you see
Good.
my screen?
We see that, but it's not yet in presentation mode.
Yeah, I'm just like now going to start. All right. So hello, everyone. I also apologize to not being actually able to present my work in person. I was really looking forward to be there, but this summer, a lot of unseen things here and visa issues. So I had to actually cancel all my international travels. But I'm very thankful that I got the opportunity to actually present virtually. So thanks a lot to organizer to giving the opportunity. So for the purpose of this conference, I decided that maybe it would be actually interesting if I some sort of give a broad view of how we can actually take a step toward doing simulation of quantum many-body systems with digital quantum processors. And a quick update as starting this summer, I also moved from IBM to Q-Control, which is another quantum company. Currently, I'm just like doing, again, a lot of algorithm and application and quantum simulation. So over the past 2 decades, there has been a lot of progress in the building quantum hardwares, and some of the frontiers of this field, you might already have heard a lot of breakthrough works from like Google, IBM, and also more from the Rydberg system, Quera, and ion trap systems. And as these systems are trying to improve in terms of actually developing their gate fidelities or increasing the number of qubits, one of the questions we as a researcher came across is that, what kind of problem, exciting problem, we can actually target with this developing quantum processors. And although in particular, maybe like 5-10 years, people really trying to push this frontiers from like, simulation of quantum material and quantum chemistry, and to quantum machine learning, and even to math finance, or more recently, probably you're hearing a lot about like, life science or even fusion energy. So, and many of this, it might be actually still open question whether the quantum computing would be able to do anything useful. But I think we could all agree that probably one of the very early and probably surely of advantage of quantum processors are in the field of quantum simulation. And if I actually look into the field of quantum simulation, in particular in quantum many-body physics, I can actually categorize the problems in 3 different branches. I think the very first one is the ground state preparation. And we know that the preparing the ground state of two dimensional system is a QMA hard. And there are, although different, classical approximation like DMRG or quantum Monte Carlo has been developed, but each of them can actually have challenges in particular regimes. And I think that this has been one of the promising candidate for, preparing the ground state on quantum simulator and, probing their properties. The second one that probably is the most straightforward one and probably the most easiest one that has been also pretty much explored a lot is the dynamical properties, right? If we actually look at the quench dynamics of some physical system, because it's just going to be a unitary evolution, which is very straightforward that you can map it to some unitary gate in your quantum processors. Although one of the limitations is to actually go to some long time, but it's still very interesting properties. If you actually increase the number of your particles, there are some interesting problems in terms of like thermalization or, disorder problems that you can actually study. And the third category after that probably are thermal state properties or thermal state actually preparation. This is also another important part of, if you want to actually look at the MBL, then the MBL physics is actually, it's not anymore a ground state. So you have to actually study the full spectrum or be able to actually prepare some other, states. Although the thermal state preparation and the ground state preparation still remain one of the most hardest problems that we know in actually quantum simulation. And although like now we are in this era that people actually call the near-term quantum processors, which means like, we have probably a couple of hundred different qubits, like maybe like superconducting qubits or like Rydberg atoms. But still, we are very far away to actually being able to probe what is known as a fault-tolerant quantum computer. However, while we actually increase the number of qubits, which is also related with the depths of also the quantum circuit complexity, we want to actually be in this region after problems that are like beyond the classical computer. But on the other hand, as actually we increase the circuit complexity, then we have to also deal with the error of the gates in the quantum processes. And these errors can actually manifest itself in different form, like you can actually have measurement errors, or you can actually have errors in the gate and the operations that we are trying to implement. And in order to be able to actually get any meaningful result from simulation of any physical system in quantum and the current quantum processes, we really need to also advance what are some of the techniques known as error suppression and also error mitigation. And generally, the error suppression, they try to actually work, so we can actually have different kind of noise, but the error suppression, they work by implementing some gate into your circuit such that you can actually average out the noise in your hardware. And another scheme that people do, so like after you actually have the circuit, you can actually do some post-processing. But the cost of this error mitigation schemes in this particular model that I'm talking about, known as a probabilistic error cancellation, is that you can actually have you need to actually prepare many different circuits. So, and the final one is actually error mitigation of the measurement. So that's quite actually easy, but there are other methods known as zero noise extrapolation that you actually in purpose try to amplify the noise in your quantum circuit. And you try to extrapolate to the zero noise and try to estimate the observable that you want. And the last one, as I mentioned, it was just like probabilistic error cancellation, means that you're trying to actually get an estimate of some observables, but you prepare many different circuits, and you try to probabilistically sample from those different circuits such that in the end you will actually get a faithful value for your observable. So that's kind of I wanted just to give you some idea of what are the challenges we deal with if you want to actually try to look at and investigate some properties of many-body systems in quantum processors. However, over the past few years, we have seen that there is some amount of different physical system that people have studied. And in this particular case, one of the projects that I have actually done in IBM, I was interested to actually see if we can measure central charge in quantum processes. So I'm assuming many of you are already familiar, but we know that, like this is a quantity that actually appears in many different scales. So people in high energy physics, they know, and this is the one of the cornerstone of the conformal field theory. And in many body physics, we actually deal with the central charge when we actually have critical phase transition. And one of the important toolboxes that has been developed is the conformal field theory in 2 dimensions, which allows us to actually obtain different properties of the system at the critical point. And one of the cornerstone of the conformal field theory is the central charge. And as I was saying, so the central charge can actually appear in different quantities, for example, in the 2-point correlation functions of energy momentum tensor, or in the free energy. And more recently, as I mentioned, like recently, this is about now 20, 30 years, people have also seen the footprint of the central charge also in the entanglement entropy. Which actually shows as a scaling behavior as we actually look at the entanglement entropy at the critical points of one-dimensional quantum spin chains. But despite that, one of the interesting things was that like no one was able to directly or indirectly measure the central charge in any experiment. And if we actually look into some of the reason why, because in the context of many body physics, people actually studied the central charge scaling using the entanglement entropy, which usually calculated by calculating, actually, if you take a system and you have the subsystem and you trace over the rest of the system, and we can calculate the entanglement entropy by looking at the reduced density matrix. But the entanglement entropy usually calculated in the Schmidt basis, which is something non-intuitive and not physical for anything to be done in the experiment and in the lab. And if you want to actually calculate it, usually I'll have to actually do a full state quantum tomography to be able to reconstruct the quantum state and also then calculate the reduced density matrix. So that kind of gives you the hint why the central charge has not been actually measured. But on the other hand, people were interested to actually look at some other kind of entropies. And there were a lot of studies that now, instead of actually looking at the entanglement entropy, which you calculate the reduced density matrix, but now we can actually take the system and again, extract the subsystem. But now we actually look at the projection of the reduced density matrix in some local basis. So for example, this can be actually in the Z basis, and we can measure the probabilities in the Z basis. And from those probabilities, we can now actually calculate the Shannon entropy or the higher moment of heterogeneity entropy. And this has been actually also extensively studied. So in terms of the entanglement entropy, as I mentioned, it is known that at the critical point, there is this scaling behavior for the infinite system chain, that the coefficient of the log of the subsystem size is actually scales with the central charge. The similar things also has been extensively numerically been studied for the Shannon entropy. For different boundary condition, open boundary condition, finite system, or periodic boundary condition over different, like quantum spin chains, like transphasing model or XXC. But one of the open question also in terms of the Shannon entropy is that we don't still know that, first of all, the Shannon entropy is the volume, no, although a lot of numerical studies suggest that the subleading term actually has the logarithmic behavior. But the coefficient of the Shannon entropy, the second one, still there is no kind like a mathematical proof that is related to the central charge. And I can tell you why this is difficult, because essentially once you actually have the Shannon entropy, now you have to calculate each of all these different L like a configuration that you get for the subsystem. You have to find how the probability of those, a specific configuration will change within your conformal field theory. And essentially this becomes a really hard problem. But although this is still like theoretically open question, from just the conformal fit theory. We know that still there is a lot of numerical studies suggested that the Shannon entropy would actually have some indication of the central charge, in particular the higher moment, that the numerical accuracy has been more rigorous. And that actually gives this idea, because if I actually work with the Shannon entropy in the local basis, then that is something that I can think about to prepare the state in the quantum, processors and do local measurement. And from the measurement, I can actually, like extract the different statistic and look at the Shannon entropy, and then, repeat the experiment for the different system size and extract the central charge. So this is in a nutshell, like what is actually happening in the experiment. And one of the methods that currently we can actually do ground state preparation for quantum simulator, it's variational quantum algorithm, which means that you're trying to variationally find what kind of angles you have to implement in your quantum circuit, such that in the end, you can actually get a faithful quantum state. So these are actually the different steps that we have to take into account. One, the very first thing is that you need to faithfully prepare your ground state on the quantum circuit. But of course, even after that, when you try to implement or run the experiment, you will deal with the noise. So we actually need to learn the noise and do the error mitigation, for which we similarly did the combination of the error mitigation and the suppression that I mentioned earlier. And finally, after doing the local measurement in the Z or X spaces, we can actually try to find the scaling behavior of the central charge from the Shannon entropy. So here I'm going to talk about like the very first experiment we did. We prepared the ground state of the transfer field Ising model. And from the local measurement in the Z basis, what is nice about transfer Ising model, that this is a stochastic local Hamiltonian, which means that the off-diagonal matrix elements, they are real and non-positive. And this implies that actually from the probabilities that you get in some local basis, you would be able to reconstruct the quantum state. So we did the experiment for the finite system size and calculating the entanglement entropy when you actually have the subsystem, chosen from the left or the right-hand side in the middle. And the expectation is that for this particular boundary condition, we have to actually get the entanglement entropy to behave with a logarithmic. And this Cn, it has like this coefficient. So these are actually obtained from the numerical studies for different quantum spin chain. On the most part in the A, I'm actually showing what is the ground state, fidelity of the ground state we actually get from just like, implementing the variational algorithm. So this already gives us, in terms of the energy and also the state itself fidelity, a very good fidelity. So that's how we obtain the angles of the gates that we have to implement in the hardware. And on the part B, this is one of the quantum processors that we actually choose our qubits out of it. So these are actually done for 10 qubits with the open boundary condition. So this was the layout that we actually used. And this like different color, they're just like for the error mitigation. So I'm not going to go too much into the detail of it. But on the bottom part C, I'm actually showing you the experimental result from the hardware that we actually implement the 10 qubits. And as you can see, the exact result is shown with the blue square over here. And the experimental data that we get is quite, de-amplified because of the noise in the hardware. And after we actually do the error mitigation schemes, we can actually recover most of the, we can actually recover the signal that we require to estimate the entanglement entropy. And from the observable, this is in the Z measurement, we calculate the entanglement entropy. As I mentioned, from the Z measurement, you can actually reconstruct the full quantum state. And once you have the full quantum state, you calculate the radius density matrix, and then you also look at the entanglement entropy. And as we can see, more or less the exact diagonalization result, because this is quite a small system size, you can do ED. So, and your experimental result is actually, they have a good agreement. But then we wanted to actually also repeat it for the different, n. This n is actually the moment of the Rayleigh entropy, which means that what is the probabilities you are taking to the power of n. But in general, for the open system, we see huge finite size effects. So that's actually, I wanted to actually emphasize. So just looking at the finite size effects, this is the derivatives of the sigma z, because you could have actually tell me, but look, like the system size of 10 open boundary condition, you should have actually see a lot of finite size effect. And that's actually true. That's actually shown by the derivative, as we see that it's deviated from what should be actually around 1 with the periodic boundary condition. This is just the top row indicating that maybe we should actually look at the periodic boundary condition. And on the bottom, I'm actually showing the result after implementing a periodic boundary condition with the 12 spins on the quantum processors. The top blue are the result that we actually get from the exact, and the experimental result I'm showing with the green one. And this I is actually the mutual Rayleigh entropy, means that we actually kind of get rid of the constant volume term, and we look at the subleading term directly. So for the mutual Rayleigh entropy, we also repeat it for different moment of 2, 4, and 6. And this is actually what we observe for the transfer easing model. The central charge, the universality class for the transfer easing model, that should be actually equal to half. And what we observe is that, like, we still have some sort of error because of the noise and all that, but that is as best as we can do for the transfer easing model, periodic model. The next question we asked that, what about the other universality class? Because one of the nice things about digital quantum processors compared to maybe optical lattices is that you can directly actually implement different Hamiltonians. So if you have like the XXC Hamiltonian or maybe PXV Hamiltonian, the procedures is going to be pretty straightforward and similar. This gives you a huge amount of freedom to actually study wide class of problems in digital quantum processors. So we actually did the similar state preparation and do the measurement. Again, you can also do the measurement in the X or Z bases and look at the mutual Rayleigh entropy. And in this case, we actually see the result. One of the top one is actually in the Z bases, and one of the results is actually in the X bases. And we actually achieve a very good accuracy for the XXC Hamiltonian. So something also particular about the XXC Hamiltonian, that this coefficient of the central charge, it is known to be different also for different NC, that this N can be calculated from the parameters of the transfer easing model, which is the delta, which is the asymmetry of the XXC Hamiltonian. So that's kind of like brings me to the conclusion, more or less, because I think that like I'm almost also past the hour. So in nutshell, if I actually look at what are the interesting problems that we want to actually explore with quantum processor in the domain of many-body physics, as I mentioned, there are a lot of interesting properties. Probably the most straightforward that we can implement are the dynamical properties. Because we can just like, directly explore the time evolution of quantum systems. And as time passes, this actually becomes beyond classical approach, like time-dependent DMRG, as the entanglement grows. So maybe there are a great opportunity as the depths of the quantum circuit becomes better and better. One of the hopeful things is that we can actually study some of the time evolution. I think that we already see some interesting topics, just like probably there were more, but also in the previous talk, it's the transfer properties of one-dimensional or two-dimensional system. And in general, we can actually look at the non-Jacobian behavior, which are way more harder for a lot of classical computational schemes. And critical dynamics and also conformal fit theories, like, quench. These are actually interesting problems to explore. And probably you have already seen a long list of these studies in different quantum processors from Google, IBM, or Quera. The next one is the ground state properties. As I mentioned, the ground state usually are hard to actually prepare. And numerical solution for 1D gap model, we know that they actually follow the area law, but in 2D, that's not, a lot of methods can be actually challenging. And other interesting problems that are open in general in quantum many-body physics is actually the Fermi-Hubbard model. In 2D in particular, we know that there are a lot of studies exactly at half-filling. There are good theories, but away from half-filling, still there is no unified theory to study Fermi-Hubbard model. The same goes with topological states, or discovering exotic phases of matter like a spin liquid. And finally, also in the thermal state properties, I think still the thermalization itself, how the thermalization emerges, or like in which cases we can actually have quantum thermalization. These are all still, there are a lot of interesting open problems. And also, once we go to partition function or disordered model like MBL and spin glass, these are still, are hard problems to really understand them deeply. And this actually brings quantum simulator and quantum processor as one of the promising candidates to study them. With that, I'll probably stop. And this is actually some of the, probably give you one of the work that I have done in IBM, which was this like central charge. But there was another work that we did related to the Fibonaccianian, and some of the work that we are doing in terms of the thermal state properties, how we can actually prepare thermal state in the quantum processors and scale it to big number of qubits. And within that, actually, we use tensor network in hybrid method to assist the thermal state preparation. And finally, also with the dynamical properties, we currently looking into the emergence of the universality in the presence of the noise and the Cable-Zurich mechanism and other interesting problems. I think the list is almost like really exotic and very interesting. So I'll probably stop here so I can actually take some few questions from the audience as well.
Thanks a lot. Questions? Go.
The von-Neumann entropy has the contribution is proportional to the central charge plus some term that accounts for boundary entanglement. I wonder what is known for different boundary conditions for the entropy that you were discussing.
Yes, let me actually go. So maybe I don't have that, but so this one, definitely. So the boundary condition will actually change your coefficient, how that is actually scaling in terms of, this can be, for example, in the entanglement entropy, this is C divided by 3 or C divided by 6. So that coefficient can change. And this is exactly known only for the entanglement entropy if you actually choose the subsystem from left. Even in the finite system, if I actually choose the subsystem from the middle, I believe still that has not been proven. In the case of the Rayleigh entropy as well, the coefficient, maybe I'll actually show you. So in the case of the Rayleigh entropy as well, this C and P, because I put P over here, this is calculated for the periodic boundary condition to be C divided by 4. This is as twice if we actually look at the open boundary condition. Maybe twice or half, I might be actually.
Can also be very different, and they have contribution to what you show as gamma. In fact, it's like in von Neumann entropy, there are two different terms. So gamma and
But is this as far as I know, gamma is not universal. There is no universality in the gamma. I mean, they can be different. You actually extract them from your fitting, right? Because it's just a constant, right? But the universality, when you actually look at your scaling behavior, it is, as far as I know, at least for the entanglement entropy, for this particular setup that we're looking, it will manifest itself, the universe, the conformal, like the central charge will manifest itself only in the slope.
Okay, there are universal contribution, but when in your slide, when you show open boundary condition and periodic boundary condition, with open boundary condition, you mean open and free, is it correct?
With the open boundary condition, yes, we do like open and free, yeah. And all of this coefficient will be different for any different periodic, like for any different boundary conditions.
Right? More? Okay, if not, we can close the session, and thanks both our speakers for this online version of the session. So thanks a lot.
Thank you, everyone.
Thank you.
So with all the others, see you at 2 p.m. in the usual room.